In mathematics, a square root of a number a is a number y such that y2 equals a, in other words, a number y whose square is a. For example, 4 and -4 are square roots of 16 because 42 equals 2 equals 16. Every non-negative real number has a unique non-negative square root, called the principal square root, which is denoted by square root a, where square root is called the radical sign or radix. For example, the principal square root of 9 is 3, denoted square root 9 equals 3, because 32 equals 3 times 3 equals 9 and 3 is non-negative. The term whose root is being considered is known as the radicand. The radicand is the number or expression underneath the radical sign, in this example 9. Every positive number has two square roots. Square root a, which is positive, and minus square root a, which is negative. Together, these two roots are denoted plus or minus square root a. Although the principal square root of a positive number is only one of its two square roots, the designation, the square root, is often used to refer to the principal square root. For positive a, the principal square root can also be written in exponent notation, as a 1/2. Square roots of negative numbers can be discussed within the framework of complex numbers. More generally, square roots can be considered in any context in which a notion of squaring of some mathematical objects is defined. History. The Yale Babylonian collection YBC 7289 clay tablet was created between 1800 BC and 1600 BC, showing square root 2 and 30. Square root 2 is 1, 24, 51, 10 and 42, 25, 35 base 60 numbers on a square crossed by two diagonals. The rind mathematical papyrus is a copy from 1650 BC of an earlier Berlin papyrus and other texts, possibly the Kahun papyrus, that shows how the Egyptians extracted square roots by an inverse proportion method. In ancient India, the knowledge of theoretical and applied aspects of square and square root was at least as old as the Sulba Sutras, dated around 800–500 BC. A method for finding very good approximations to the square roots of 2 and 3 are given in the Baudhayana Sulba Sutra. Aryabhata in the Aryabhatiya has given a method for finding the square root of numbers having many digits. It was known to the ancient Greeks that square roots of positive whole numbers that are not perfect squares are always irrational numbers. Numbers not expressible as a ratio of two integers. This is the theorem Euclid x 9, almost certainly due to Theaetetus dating back to circa 380 BC. The particular case square root 2 is assumed to date back earlier to the Pythagoreans and is traditionally attributed to Hippasus. It is exactly the length of the diagonal of a square with side length 1. In the Chinese mathematical work Writings on Reckoning, written between 202 BC and 186 BC during the early Han Dynasty, the square root is approximated by using an excess and deficiency method, which says to combine the excess and deficiency as the divisor, the deficiency numerator multiplied by the excess denominator and the excess numerator times the deficiency denominator. Combine him as the dividend. Mahavira, a 9th-century Indian mathematician, was the first to state that square roots of negative numbers do not exist. A symbol for square roots, written as an elaborate R, was invented by Regiomontanus, and R was also used for radix to indicate square roots in Gerolamo Cardano's Ars Magna. According to historian of mathematics D.E. Smith, Aryabhata's method for finding the square root was first introduced in Europe by Catania in 1546. The symbol square root for the square root was first used in print in 1525 in Christoph Rudolph's Cos. Properties and uses. The principal square root function f equals square root x is a function that maps the set of non-negative real numbers onto itself. In geometrical terms, the square root function maps the area of a square to its side length. The square root of x is rational if and only if x is a rational number that can be represented as a ratio of two perfect squares. The square root function maps rational numbers into algebraic numbers for all real numbers x, for all non-negative real numbers x and y, and the square root function is continuous for all non-negative x and differentiable for all positive x. If f denotes the square root function, its derivative is given by the Taylor series of square root 1 plus x about x equals 0 converges for x1 and is given by the square root of a non-negative number as used in the definition of Euclidean norm, as well as in generalizations such as Hilbert spaces. It defines an important concept of standard deviation used in probability theory and statistics. It has a major use in the formula for roots of a quadratic equation, quadratic fields and rings of quadratic integers, which are based on square roots, are important in algebra and have uses in geometry. Square roots frequently appear in mathematical formulas elsewhere, as well as in many physical laws. Computation. Most pocket calculators have a square root key. Computer spreadsheets and other software are also frequently used to calculate square roots. Pocket calculators typically implement efficient routines, such as the Newton's method, to compute the square root of a positive real number. When computing square roots with logarithm tables or slide rules, one can exploit the identity square root equals e2 or square root equals 10^2, where ln and log 10 are the natural and base 10 logarithms. By trial and error, one can square an estimate for square root and raise or lower the estimate until it agrees to sufficient accuracy. For this technique it's prudent to use the identity 2 equals x2 plus 2xc plus c2, as it allows one to adjust the estimate x by some amount c and measure the square of the adjustment in terms of the original estimate and its square. Furthermore, 2x2 plus 2xc when c is close to 0, because the tangent line to the graph of x2 plus 2xc plus c2 at c equals 0, as a function of c alone, is y equals 2xc plus x2. Thus, small adjustments to x can be planned out by setting 2xc to a, or c equals a. The most common iterative method of square root calculation by hand is known as the Babylonian Method, or Heron's method, after the 1st century Greek philosopher Heron of Alexandria, who first described it. The method uses the same iterative scheme as the Newton-Raphson method yields when applied to the function y equals f equals x2 minus a, using the fact that its slope at any point is dy dx equals f equals 2x, but predates it by many centuries. The algorithm is to repeat a simple calculation that results in a number closer to the actual square root each time it is repeated, with its result as the new input. The motivation is that if x is an overestimate to the square root of a non-negative real number, then x will be an underestimate, and so the average of these two numbers is a better approximation than either of them. However, the inequality of arithmetic and geometric means shows this average is always an overestimate of the square root, and so it can serve as a new overestimate with which to repeat the process, which converges as a consequence of the successive overestimates and underestimates being closer to each other after each iteration. To find x, start with an arbitrary positive start value x. The closer to the square root of a, the fewer the iterations that will be needed to achieve the desired precision. Replace x by the average 2 between x and a, x. Repeat from step 2, using this average as the new value of x. That is, if an arbitrary guess for square root a is x0, and xn plus 1 equals 2, then each xn is an approximation of square root a, which is better for large n than for small n. If a is positive, the convergence is quadratic, which means that in approaching the limit, The number of correct digits roughly doubles in each next iteration. If r equals 0, the convergence is only linear. Using the identity square root r equals 2n square root 4na, the computation of the square root of a positive number can be reduced to that of a number in the range 1, 4. This simplifies finding a start value for the iterative method that is close to the square root, for which a polynomial or piecewise linear approximation can be used. The time complexity for computing a square root with n digits of precision is equivalent to that of multiplying two n-digit numbers. Another useful method for calculating the square root is the shifting nth root algorithm, applied for n equals 2 square roots of negative and complex numbers. The square of any positive or negative number is positive, and the square of 0 is 0. Therefore, no negative number can have a real square root. However, it is possible to work with a more inclusive set of numbers, called the complex numbers, that does contain solutions to the square root of a negative number. This is done by introducing a new number, denoted by I and called the imaginary unit, which is defined such that I2 equals -1. Using this notation, we can think of I as the square root of -1, but notice that we also have 2 equals I2 equals -1, and so -I is also a square root of -1. By convention, the principal square root of -1 is I, or more generally, if x is any non-negative number, then the principal square root of -x is the right side is indeed a square root of -x. Since for every non-zero complex number z there exist precisely two numbers w such that w2 equals z, the principal square root of z, and its negative square root of an imaginary number, the square root of I, is given by this result, can be obtained algebraically by finding r and b such that or. Equivalently, this gives the two simultaneous equations with solutions. The choice of the principal root then gives the result can also be obtained by using de Moivre's formula and setting, which produces principal square root of a complex number to find a definition for the square root that allows us to consistently choose a single value, called the principal value. We start by observing that any complex number x plus iy can be viewed as a point in the plane, expressed using Cartesian coordinates. The same point may be reinterpreted using polar coordinates as the pair, where r0 is the distance of the point from the origin, and phi is the angle that the line from the origin to the point makes with the positive real axis. In complex analysis, this value is conventionally written ra phi. If then we define the principal square root of z as follows. The principal square root function is thus defined using the non-positive real axis as a branch cut. The principal square root function is holomorphic everywhere except on the set of non-positive real numbers. The above Taylor series for square root 1 plus x remains valid for complex numbers x with x less than 1. The above can also be expressed in terms of trigonometric functions. Algebraic formula: when the number is expressed using Cartesian coordinates, the following formula can be used for the principal square root, where SGN is the signum function. The sign of the imaginary part of the root is taken to be the same as the sign of the imaginary part of the original number. The real part of the principal value is always non-negative, as the other square root is simply -1 times the principal square root. Both roots can be written as notes because of the discontinuous nature of the square root function in the complex plane. The law square root zw equals square root z square root w is in general not true. Wrongly assuming this law underlies several faulty proofs, for instance the following one showing that -1 equals 1. The third equality cannot be justified. It can be made to hold by changing the meaning of square root so that this no longer represents the principal square root but selects a branch for the square root that contains the left-hand side becomes either if the branch includes plus I or if the branch includes minus I, while the right-hand side becomes where the last equality, square root 1 equals minus 1, is a consequence of the choice of branch in the redefinition of square root. Square roots of matrices and operators. If A is a positive definite matrix or operator, then there exists precisely one positive definite matrix or operator B with B2 equals A. We then define A1, 2 equals B. In general, matrices may have multiple square roots or even an infinitude of them. For example, the 2 times 2 identity matrix has an infinity of square roots, though only one of them is positive definite. In integral domains, including fields, each element of an integral domain has no more than 2 square roots. The difference of 2 squares identity U2 minus V2 equals is proved using the commutativity of multiplication. If U and V are square roots of the same element, then U2 minus V2 equals 0. Because there are no zero divisors, this implies U equals V or U plus V equals 0, where the latter means that 2 roots are additive inverses of each other. In other words, the square root of an element, if it exists, is unique up to a sign. The only square root of 0 in an integral domain is 0 itself. In a field of characteristic 2, an element has either one square root, because each element is its own additive inverse, or does not have any at all. In a field of any other characteristic, any non-zero element either has 2 square roots, as explained above, or does not have any. Given an odd prime number p, let q equals p for some positive integer e. A non-zero element of the field fq with q elements is a quadratic residue if it has a square root in fq. Otherwise, it is a quadratic non-residue. There are 2 quadratic residues and 2 quadratic non-residues. 0 is not counted in either class. The quadratic residues form a group under multiplication. The properties of quadratic residues are widely used in number theory, in rings in general. In a ring we call an element B a square root of a if B2 equals A. To see that the square root need not be unique up to sign in a general ring, consider the ring from modular arithmetic. Here, the element 1 has 4 distinct square roots, namely plus or minus 1 and plus or minus 3. On the other hand, the element 2 has no square root. See also the article quadratic residue for details. Another example is provided by the quaternions, in which the element minus 1 has an infinitude of square roots including plus or minus I, plus or minus j, and plus or minus k. In fact, the set of square roots of minus 1 is exactly, hence this set is exactly the same size and shape as the unit sphere in 3 space. The square root of 0 is by definition either 0 or a zero divisor, and where zero divisors do not exist, it is uniquely 0. It is not necessarily true in general rings, where z, n2z for any natural n provides an easy counterexample. Principal square roots of the positive integers. As decimal expansions, the square roots of the perfect squares are integers. In all other cases, the square roots of positive integers are irrational numbers, and therefore their decimal representations are non-repeating decimals. Note that if the radicand is not square-free, then one can factorize, for example, and as expansions in other numeral systems, the square roots of the perfect squares are integers. In all other cases, the square roots of positive integers are irrational numbers, and therefore their representations in any standard positional notation system are non-repeating. The square roots of small integers are used in both the SHA-1 and SHA-2 hash function designs to provide nothing up my sleeve numbers. As periodic continued fractions, one of the most intriguing results from the study of irrational numbers as continued fractions was obtained by Joseph Louis Lagrange c. 1780. Lagrange found that the representation of the square root of any non-square positive integer as a continued fraction is periodic. That is, a certain pattern of partial denominators repeats indefinitely in the continued fraction. In a sense, these square roots are the very simplest irrational numbers, because they can be represented with a simple repeating pattern of integers. The square bracket notation used above is a sort of mathematical shorthand to conserve space. Written in more traditional notation, the simple continued fraction for the square root of 11, 3, 3, 6, 3, 6 looks like this, where the two-digit pattern, 3, 6, repeats over and over again in the partial denominators. Since 11 equals 32 plus 2, the above is also identical to the following generalized continued fractions. Geometric construction of the square root. The square root of a positive number is usually defined as the side length of a square with the area equal to the given number, but the square shape is not necessary for it. If one of two similar planar Euclidean objects has the area a times greater than another, then the ratio of their linear sizes is square root a. A square root can be constructed with a compass and straight edge. In his Elements, Euclid gave the construction of the geometric mean of two quantities in two different places, proposition 2, 14 and proposition vi, 13. Since the geometric mean of A and B is, one can construct simply by taking B equals 1. The construction is also given by Descartes in his La Géométrie, see figure 2 on page 2. However, Descartes made no claim to originality and his audience would have been quite familiar with Euclid. Euclid's second proof in Book Vi depends on the theory of similar triangles. Let AHB be a line segment of length A plus B with R equals A and HBE equals B. Construct the circle with AB's diameter and let C be one of the two intersections of the perpendicular chord at H with the circle and denote the length CH as H. Then, using Thaler's theorem as in the proof of Pythagoras' theorem by similar triangles, triangle AHC is similar to triangle CHB so that RCH is as HC, HB, i.e., from which we conclude by cross-multiplication that and finally that. Note further that if you were to mark the midpoint O of the line segment AB and draw the radius OC of length, then clearly OC greater than CEH, i.e., which is the arithmetic geometric mean inequality for two variables and, as noted above, is the basis of the ancient Greek understanding of Heron's method. Another method of geometric construction uses right triangles and induction. Square root 1 can, of course, be constructed, and once square root x has been constructed, the right triangle with 1 and square root x for its legs has a hypotenuse of square root x plus 1. The spiral of Theodorus is constructed using successive square roots in this manner.